Okay guys, let's continue our solution to the last problem we solved. So let us solve now requirement C, in which we are asked at one point are the stirrup no longer required theoretically. So before we proceed with the calculation, let's look into this figure here, wherein there are three graphs of shear equations we have. No? So this red graph here, which has an equation Vux equals R1 minus Wux, actually represents your factored shear forces, um, which is actually measured from the left support up to the point where the shears become zero. So this is actually uh, at the midspan. Okay. So for the second graph of the shears equation, this curve here, which actually represents a flat line and then suddenly has a decreasing value here, which is uh, negatively decreasing in slope, okay, is actually the equation in which the representation is a detailed equation in this form given by the equation here. Okay, so this is the equation that we refer to as your detailed equation. Okay, and for the last equation here, which is the green one, is the simple equation we use on a day-to-day basis, which is a simple equation given to us by the ACI or the NSCP in this form. So this is now actually your simple shear equation. Okay, so we will now be solving the possibility of the point of intersection using both the detailed and the simple equation based on the reference equation, which is the factored shear equation here. Okay, so we know in our elementary algebra and calculus that whenever we want a point of intersection, we simply equate, okay, the working equation that represents both the detailed and the factored equation and the simple and the factored equation. So for your letter C, this point X here, which represent the intersection at which the detailed equation and the factored shear equation meets, actually represents the point at which the stirrup are no longer required beyond this point. So it simply means that beyond this line here, okay, so beyond this line, stirrups are no longer required. But of course, so we are only talking about theoretical situations. Okay, So in actual practice, we still have to put some stirrups for purpose of increasing our safety, our factor of safety. Okay, and also here in this simple equation, the point in which beyond which stirrups are no longer required actually is referred to this line here. Okay, so that is the physical interpretation of what we are going to do in this next computation. Okay, remember that this point now is simply the point which is the midspan of your simply supported beam. And this is exactly at L over 2 distance, which is 3 meters. Okay, take note that to solve the distance x from the face of the support, we simply equate the shear capacities, which are the detailed and the simple equation of shear, with that of the factored shear equation, which is in the form R1 minus WUX. Hence, if we do that, we simply get the detailed equation VC, which is in this form, okay? And then equate it. Of course, we have to multiply this later with phi, okay? But before we do that, we simply take note of this value here, and this value here simply represents your reciprocal of the A over D ratio. Okay, so this value here is actually the VUD over MU, okay, that we are computing. Okay, and of course we take note that your value of VU and MU must be computed at an unknown distance of x, which is the required uh, variable in this particular problem. Okay, so we cannot get an absolute value for your VUX and MUX. Rather, we will be having a value which is in the form of a function of x. So VU at x distance is simply R1, which is 360, minus 120x. Okay, and take note that again, the moment at that point can also be computed by simply getting the area of the trapezoid. So this is now the area of the trapezoid that represents, okay, your moment at the point in which the stirrup are theoretically not required. Okay, so area of the trapezoid. Okay, so this is 1/2 of your VU maximum, and the VU maximum here is simply the reaction. Okay, so this value here for this particular case is simply your R1. And then the value here is simply the value of the shear that we have computed on the basis of this equation at an unknown distance of x. So we just plug it here. Okay, so MUX is VUM max, which is 360, and then VUX is 360 minus 120x times quantity x. So I think I have an error here in our last video wherein I substituted a value of the length equal to 12. No, so that's why this became 720, so, and that is actually wrong. Okay. Because I use L equals, I think, 12. Okay, so this is wrong. L is only 6 meters. So I apologize for such error. Okay. Okay, so BWD here is actually given, so we have no problem with this. And of course, we do this by simply, we have to simplify this further using algebra, but since I'm using MathCAD, I don't need to simplify it. So if you are using a powerful calculator class, then I think this is also manageable. So all you have to do is to equate this phi, okay, VC. So I now uh, uh, inserted or substituted the value of phi VC here, okay, and then my VUX is substituted here, okay. So I equate it. So if you don't have a calculator, you need to simplify. But since I have a powerful tool here in MathCAD, I simply equate them and just make a command to find x by assuming x equals 1. Note that x is in meter now, no? So in this unit, my x will be automatically yield the unit of meter. So I get 1.923, okay? So in your exercise later, I want you to do it manually. And if you have some problems with it, we can discuss it. But for now, that's not important. What is important is for you to know the principle behind answering the question inside the problem on this context. Okay. So note that if you use a simple equation, the calculation will be simpler. So in here, I use a simple equation instead of the detailed equation. So I just plug in 1 over 6 square root of FC prime BWD times phi. I get 1.86. And this can be solved very easily by solving this value. And then we can take note of x is simply equal to, okay, phi times 1 over 6. All are given F prime C BWD. Okay. I think this is negative. So let's put this on the other side. Okay. So x is equal to 360 minus divided by 120. Okay. Okay, so this is minus p. So you just get this value and you will obtain 1.86. Okay, and the values are not very far from each other. Taking note that the error is only very small. So that's why in a day-to-day basis, the simple equation can be used as a reference equation. But if you have a good tool, a program, you can better off solve the problem using the detailed equation. So again, at what point is the minimum air stirrups AV minimum is required? So what happens is the procedure will only shift from considering one half of the detailed equation. So I have here a dotted curve and a dotted line. So this represents one half of the detailed equation. Okay, so uh, this value here, this dotted, okay, let's put it here. Okay, so this equation here is simply one half of phi VC, where VC is the detailed equation. Okay, So instead of having a full value of the capacity, we get 1/2. Also, for this straight line, this green here, okay, this green, okay, so let's put it here. This, okay, let's use another color. Okay, so this represents 1/2 of VC, where VC is the simple equation. Okay, so again, what we will be computing now are no longer this x, but rather this x's. So I will shift my x from here. It will now be measured up to here. Okay, so my x will be extended there quite longer, and my x here will be extended up this. Okay, so these are the new point of intersection that I am computing on the basis of the AV requirement. Okay, so this is now uh, solving for the AV minimum requirement. So if you are asked, where do you place the minimum requirement? It is beyond these 2 points that at least the minimum requirement must be satisfied. Okay, the dotted lines are 1/2 the values obtained from the shear equation, which are the detailed and the simple shear capacities. Okay, so all you have to do again is just to plug in your value of DC and V, but this time you just divide it by 2 is equal to VUX. Okay, so take note, the procedure is the same except for the capacity, which is taken in terms of 1/2 VVC. Okay, VU is still the same, MUX still the same. Only here in the equation again we consider 1/2 of VBC. So using again a MathCAD tool, I obtained from the detailed equation a value of 2.49. So this is in meters. Okay, so this is already in meters because your X is already in meters there. Okay, so this is in meters here. Again, this is your consideration for your detailed equation. And note that if we use again the simple equation, the calculation above will be much simpler. And you can calculate this manually very easily by again um, taking into consideration only 1/2 of this value. Okay, so how do we do it? So x now is simply equal to 360 minus phi over 2. Okay, so we have a 2 there, and then 1/6 square root of f prime c bwd. Okay, and then divided by 120. Okay, and that will give you a value of 2.43. Okay, so that's it for letter C and D. They are almost similar, only with some consideration in the code requirement that they became different. So thank you. For now, we will be discussing the requirements for letter E and F on the next video. Thank you.